This video is actually a section of a course. This section includes the following lessons. First, concept of files, persistent data. Second, opening and closing files, using file pointers and the fopen, fclose functions. Third, basic file reading and writing, using fprintf and fscanf for formatted I/O. Fourth, exercises, no answers. This lesson does not include the answers. Okay, let's get started. One, Introduction, the problem of volatility. Up until now, all the data we've used in our C programs, variables, arrays, structs, has been volatile. Volatile data means the data only exists in the computer's RAM, random access memory, while the program is running. As soon as the program finishes, crashes, or the computer is turned off, all that data is completely erased. Think about a text editor. If you type a 1,000-word report but forget to save, all that work is lost when you close the application. That's volatile data. 2. The solution, persistent data with files. To store data permanently, we use files. A file is a sequence of bytes stored on a non-volatile storage device, such as a hard disk drive, HDD, or solid-state drive, SSD. Persistent data means the data remains available even after the program stops executing and the computer shuts down. By using files, your C programs can achieve real-world functionality, saving game scores, storing user configurations and settings, logging error messages, managing large databases of customer or inventory records. 3. Files versus variables, the core difference. 4. Two types of files in C. In C, we generally categorize files into two types based on how the data is stored and interpreted. A. Text files, human-readable. Content. Store data as a sequence of ASCII or Unicode characters. Reading. You can open and read a text file using a standard text editor, like Notepad or VS Code. Examples, configuration files, .cfg, log files, .log, or simple text documents, .txt. Drawback. Storing the integer 123 takes 3 bytes, 1, 2, 3, plus maybe a new line character. B. Binary files, computer-readable. Content. Store data exactly as it is represented in the computer's memory, as raw binary bytes. Reading. Cannot be read directly with a text editor. The data will appear as garbage characters. Examples, executable programs, .exe, images, .jpg, or compressed data archives. Benefit, highly efficient. Storing the integer 123 takes only 4 bytes for a standard integer, regardless of how many digits it has, resulting in smaller files and faster read-write times. 5. File stream, the communication channel. When your C program needs to interact with a file, it doesn't access the file directly. It uses an abstraction called a file stream. A stream is a sequence of bytes flowing between a program and a device, in this case, a disk file. When you want to use a file, your program must establish a link to the file on the disk, opening the stream, operate on the stream, reading or writing data, close the link, closing the stream, which saves all changes and frees up resources. This stream is managed by a special type of pointer provided by the C standard library. 6. Conclusion and next steps. We now understand why files are essential. They provide persistence for data, allowing information to survive beyond the program's execution. In the next lesson, we will get practical and learn how to use the C standard library functions to create and destroy that vital link between our program and the file on the disk. Our next lesson is 8.2. Opening and closing files, using file asterisk pointers and the fopen, fclose functions. One. Introduction, the file handle. In the last lesson, we learned that to achieve persistent data storage, we must interact with disk files via a stream, a sequence of bytes. To manage this stream, the C language uses a special type of pointer called a file pointer. About the file pointer, the file type is a struct defined in the stdio.h library. It holds all the necessary administrative information about the file: its current position, its mode, reading, writing, and status indicators. Because we interact with this structure via its memory address, we must declare it as a pointer, file*file ptr. This file pointer is your file handle, the way your program can access and manipulate the file on the disk. 2. Opening a file, the fopen function. The fopen function performs the critical task of locating the file on the disk, establishing the stream, and returning the file handle to your program. Here is the prototype of the fopen function. You can image the prototype like here. Parameters: file name, a string containing the name of the file, e.g., data.txt. Mode, a string specifying how you intend to use the file, read, write, append, etc. What file modes you can use: here are the common file modes. The mode R is to read. If the file exists, it will start reading from the beginning. If the file does not exist, the function returns null. Next, the mode W is to write. If the file exists, it will destroy existing content and start from the beginning. If the file does not exist, it will create a new file. And the mode A, this is to append. If the file exists, it will start writing at the end of the file. But if the file does not exist, it will create a new file. Next is code example, opening for writing. Three. Error checking, the null return. When fopen fails to open a file, for example, trying to read a file that doesn't exist, or lacking disk permissions, it returns the special pointer value null. You must always check if the file pointer is null immediately after calling fopen to ensure your program doesn't crash when trying to use an invalid handle. 4. Closing a file, the fclose function. Once you are finished reading or writing, you must close the file stream using the fclose function. You can image the prototype like here. So why closing is vital? First, data flush. Most C systems buffer write operations. They keep data in RAM temporarily. Fclose ensures that all remaining buffered data is safely written or flushed to the physical disk. If you don't close, you risk losing data. Second, resource release. It frees the system resources and makes the file available for use by other programs. Next is code example, closing the file. Five. Conclusion and next steps. You've learned the 2 essential steps for file management. About the open step, use fopen to establish a connection and get the file pointer. Always check for null. And about the close step, use fclose to ensure data is saved and resources are released. In the next lesson, we will finally use these functions to move data. We will explore 8.3, basic file reading and writing, using fprintf and fscanf for formatted I/O, which are the file equivalents of the printf and scanf functions you already know. One. Introduction, the file I/O equivalents. In the previous lessons, we learned how to establish and terminate the connection to a file using fopen and fclose. Now that we have the file handle, file pointer, we can actually move data. The C standard library provides functions that are almost identical to the standard console, I/O functions you already know, but with one key difference. They require the file pointer as their first argument. Today we focus on fprintf, writing formatted data to a file, fscanf, reading formatted data from a file. 2. Writing to a file, the fprintf function. The fprintf function is used to write formatted output, like strings, integers, and floats, to the file pointed to by the file handle. You can image the prototype of fprintf function like the one on the screen. But if you want to see the actual prototype, you can see here. Next is key difference from printf function. The first argument is the file asterisk stream, our file handle. Instead of sending the output to the standard output, the console, it sends the output to the specified file. Next is code example. This code demos writing data. Let's write a few variables to a file named records.txt. When you open records.txt after running this program, you will see the exact line. ID 101, name Alice, score 95.50. Awesome, right? So, how to write many lines? And so how to append a line or many lines to an exist file. Three, reading from a file, the fscanf function. The fscanf function is used to read formatted data from the file pointed to by the file handle. It reads until a whitespace character, a matching data type, or the end of the file is reached. You may image the prototype like the one on the screen, but if you want to see the actual one, you can see here. So, what is the key difference from the scanf? Again, the first argument is the file asterisk stream. It takes input from the specified file instead of the standard input, the keyboard. Next, we have a code example. This code demos reading data. Now, let's read the data we just wrote. Note that we must open the file in read mode, R. So, how to read many lines? 4. fscanf return value, end of file OF. The fscanf function is crucial because it returns the number of items successfully read. If you expect to read 3 integers, and fscanf returns 3, the read was successful. If you are at the end of the file, EOF, and try to read, fscanf returns the special constant EOF, end of file. This feature is typically used in a loop to read every line in a file. 5. Conclusion and next steps. You have now learned the complete cycle of basic file management. Declare the handle, file pointer, open the stream, using file pointer and fopen function. Perform use fprintf to write or fscanf to read. Close the stream. Call fclose function and pass file pointer to it. This action is to save and release resources. This concludes our theoretical lessons on file management. Our next session is 8.4. Exercises, no answers. This code can help you. Problem 1. Read integers from the file input.txt, knowing that the first line is an integer representing the number of integers to read. The second line is a sequence of integers to read. Example, input.txt. Requirement. Find the largest element in the array of integers and write it to the file output.txt. Problem 2. Read integers from the file input.txt, knowing that there is only one line containing the integers. Example, input.txt. Requirement. Find the Armstrong numbers in that array of integers and write them to the file output.txt. Problem 3. Read integers from the file input.txt, knowing that there is only one line containing the integers, and each integer is separated by a comma. Example, input.txt. Requirement. The file gcd.txt stores one integer which is the greatest common divisor of all elements in the array. The file lcm.txt stores one integer which is the least common multiple of all elements in the array. Problem 4. Data in the file input.txt consists of the following information. First line, the number of fractions. The following lines. Each line contains information about one fraction. Requirements. 1. Simplify the fractions and save them to the file simplifiedfractions.txt. 2. Find the largest fraction. The result should be written to the file output.txt. Example, input.txt. Output.txt. Problem 5. The format in the student.txt file is as follows. The first line contains information about one student. Full name, student ID, date of birth, a string in day, month, year format. The second line is the number of subjects. The following lines are plus list of subjects and corresponding grades. Example, student.txt. Requirements. 1. Read data from the student.txt file. 2. Enter a student's name and print to the screen the information of the student whose name matches the name being searched for. 3. Save to the file birthyear.txt the information of students whose birth year YYYY is entered from the keyboard. 4. Save to the file greatestgrade.txt the information of each student and the subject with the highest grade for each student. 5. Read data from the file greatestgrade.txt and save to the file count.txt the total number of subjects currently available for all students.